because in changing one physical state of a substance to different physical state of that substance, some heat is absorbed or evolved. For example, if liquid water is converted to water vapor, some heat is absorbed. Let us have a look on this example. Gaseous hydrogen plus half O2 gaseous gives you H2O gaseous, then delta H for this reaction is minus 57.8 kilocalories. But if gaseous hydrogen plus half O2 gaseous gives you H2O liquid, this equation is used. Delta H for this equation is minus 68.32 kilocalories. You can see that the difference between these two equations is that in first equation gaseous H2O is produced, but in second equation liquid H2O is produced. But heat of reactions in both the reactions is different. This is because some heat is evolved when gaseous water is converted to liquid water. Therefore, heat of reaction of second reaction is higher than the heat of reaction of first reaction. The second factor which influence heat of reaction is the use of different allotropic forms of a substance in a reaction. As some heat is evolved or absorbed in converting one allotropic form of a substance to the other allotropic form of that substance, hence heat of reactions are different if different allotropic forms of the same substances are used. Have a look on this example. If carbon in diamond form is oxidized in presence of oxygen to give carbon dioxide, enthalpy of reaction or heat of reaction is minus 94.3 kilocalories. But if carbon in amorphous form is oxidized in presence of gaseous oxygen to give gaseous carbon dioxide, heat of reaction or enthalpy of reaction is minus 97.6 kilocalories. The difference between the two values is equal to the heat absorbed when carbon in diamond form is converted to carbon in amorphous form. Hence, when carbon in diamond form gets converted to carbon in amorphous form, the heat absorbed will be equal to 3.3 kilocalories. One other factor which influences the heat of reactions is whether the substances used are in solid form or in solution or aqueous form. When a substance is dissolved, heat is evolved or absorbed, hence heat of reaction changes if the substance is taken in solid or in aqueous or solution form. You can have a look on the example when H2S reacts with iodine. If gaseous H2S reacts with gaseous iodine to give Hi plus sulfur, enthalpy of reaction or heat of reaction is minus 17.2 kilocalories. But if gaseous H2S reacts with aqueous iodine to give aqueous Hi plus sulfur, delta H of reaction or enthalpy of reaction is minus 21.93 kilocalories. Temperature is another very important factor which influences heat of reactions. Heat capacities depend on temperature, hence temperature is to be specified at which the reaction is carried out. Delta H2 minus delta H1 equal to N delta Cp multiplied by T2 minus T1. Here, if T1 is first temperature and T2 is second temperature, then delta H1 is the enthalpy at constant pressure at first temperature and delta H2 is the enthalpy at constant pressure at second temperature, and delta Cp is the change in heat capacity at constant pressure between the limits of these two temperatures. There is another equation, delta E2 minus delta E1 equal to N delta Cv multiplied by T2 minus T1. Here, if T1 is lower temperature and T2 is higher temperature, then delta E1 is the heat of reaction at constant volume at lower temperature and delta E2 is the heat of reaction at constant volume at higher temperature. N is number of moles and delta Cv is the change in heat capacity at constant volume between the limits of these two temperatures T1 and T2. The conditions whether the reaction has been carried out at constant pressure or constant volume also influences the heat of reactions. At constant pressure, delta H shows the heat of reaction, and at constant volume, delta E shows heat of reaction. Normally, if reactants and products are solids or liquids, the difference between these two types of heat is negligible, but it is appreciable if the reactants or products or both are in gaseous forms. Numerically, it can be said that delta E plus delta N are T equal to delta H, where delta E is heat at constant volume and delta H is heat at constant pressure. Therefore, it can be said that QV plus delta N R T equal to QP. Now, we will explain enthalpy of formation or heat of formation. When 1 mole of a substance is formed from its constituent elements in their standard state, then the process is known as formation, and the heat evolved or absorbed when 1 mole of the substance is formed from its constituent elements is called the heat of formation or enthalpy of formation of that substance. There is an example: if amorphous carbon and oxygen reacts to give 1 mole of gaseous carbon dioxide, then heat of reaction for this reaction is equal to minus 97.6 kilocalories per mole. As 1 mole of carbon dioxide has been formed from its constituent elements, hence this heat of reaction is also heat of formation or enthalpy of formation of carbon dioxide. There is another example: if gaseous hydrogen reacts with gaseous chlorine to give 2 moles of gaseous HCl, then heat of reaction is minus 44 kilocalories. This heat of reaction is not the heat of formation of HCl because 2 moles of HCl are formed here. Therefore, heat of formation of HCl will be equal to minus 44 divided by 2, that is minus 22 kilocalories. The enthalpy of formation from its constituent elements when all the constituent elements are in their standard state of temperature and pressure, that is at 25 degrees Celsius or 298 Kelvin and 1 atmosphere pressure, then the heat of formation or enthalpy of formation is known as standard heat of formation or standard enthalpy of formation. This standard heat of formation is denoted by delta H naught F at constant pressure and delta E naught F at constant volume. It is very difficult to determine the absolute values of enthalpies of substances, but relative values of enthalpies of substances can be calculated if the enthalpies of substances or standard enthalpies of substances of elements in their standard state is arbitrarily taken to be 0. Consider the reaction between solid carbon and gaseous oxygen at 1 atmosphere pressure and 25 degrees Celsius. Here is the reaction: solid carbon plus gaseous oxygen gives you gaseous carbon dioxide. Here, heat of reaction or heat of formation of carbon dioxide is given to be equal to minus 393.5 kilojoule. For the reaction solid carbon plus gaseous oxygen giving you gaseous carbon dioxide, heat of reaction will also be equal to heat of formation of carbon dioxide, which is equal to minus 393.5 kilojoules. As the enthalpy of elements in their standard state is taken to be 0, therefore, enthalpy of reactants, that is enthalpy of solid carbon and enthalpy of gaseous oxygen is equal to 0. Therefore, delta HF, which is equal to delta H, is equal to enthalpy of products, which is the enthalpy of carbon dioxide. Therefore, the enthalpy of carbon dioxide is also equal to the enthalpy of formation of carbon dioxide in standard states. The compounds which have positive enthalpy of formation are called endothermic compounds, and these are less stable than their constituent elements. And the compounds which have negative enthalpy of formation are called exothermic compounds, and these are more stable than their constituent elements. The knowledge of standard heat of formation is useful because heat of reactions can be calculated by using heat of formations of different substances. Delta H naught for the reaction will be equal to sum of the standard heats of formation of products minus sum of the standard heats of formation of reactants. Intrinsic energy is the additional amount of energy which 1 gram mole of compound possesses above that of its constituent elements. Let us have an example. Solid carbon plus gaseous oxygen gives you gaseous carbon dioxide. Here delta H of reaction, that is enthalpy of reaction, is minus 94.38 kilocalories. It means when 1 mole of carbon dioxide is formed from its constituent elements, its energy is 94.38 kilocalories less than its constituent elements solid carbon and gaseous oxygen. This is the intrinsic energy of carbon dioxide. If we assume the intrinsic energy of free elements in their standard state to be equal to 0, then the intrinsic energy of the compounds can be calculated in form of enthalpy of formation of that compound. Hence, internal energy of the substance and intrinsic energy of the substance should not be confused. Now we are going to discuss an example to calculate heat of formations and heat of reactions. Calculate the enthalpy change for following reaction. CH4 gaseous plus 2O2 gaseous gives you CO2 gaseous plus 2H2O liquid. Given that enthalpies of formation of CH4, CO2 and H2O are minus 74.8 kilojoules per mole, minus 393.5 kilojoules per mole and minus 286.2 kilojoules per mole respectively. As you know that delta H naught of the reaction is equal to delta H naught of products minus delta H naught of the reactants. Therefore, delta H naught of reaction will be equal to delta H naught formation of carbon dioxide plus 2 into delta H naught formation of H2O minus delta H naught formation of CH4 plus 2 into delta H naught formation of oxygen. You will get minus 393.5 plus 2 into minus 286.2 minus 74.8 plus 2 into 0. It is because the heat of formation of oxygen will be equal to 0. Therefore, delta H naught of reaction will be equal to minus 891.1 kilojoule. There is another example to relate heat of formations and heat of reaction. The standard heats of formation at 298 Kelvin for CCl4 gaseous, H2O gaseous, CO2 gaseous and HCl gaseous are minus 25.5, minus 57.8, minus 94.1 and minus 22.1 kilocalories per mole respectively. Calculate delta H naught at 298 kelvins for the reaction CCl4 gaseous plus 2H2O gaseous giving you CO2 gaseous plus 4HCl gaseous. Here also you know that delta H naught of reaction will be equal to delta H naught of products minus delta H naught of reactants. Hence, putting all the values, we will get delta H naught equal to delta H naught formation of carbon dioxide plus 2 into delta H naught formation of HCl minus delta H naught formation of CCl4 plus 2 into delta H naught formation of H2O. You will get minus 94.1 plus 4 into minus 22.1 minus 25.5 plus 2 into minus 57.8. Calculating, you will get delta H naught equal to minus 41.4 kilocalories. If heat at constant pressure, that is delta H, is given, heat at constant volume, that is delta E, can be calculated. Here is another example to calculate delta E when delta H is given. The molar heat of formation of ammonium nitrate, that is NH4NO3, is minus 367.5 kilojoule, and those of N2O gas and H2O liquid are plus 81.46 kilojoules and minus 285.78 kilojoules respectively at 25 degrees Celsius and 1 atmospheric pressure. Calculate the delta H and delta E for the reaction. NH4NO3 solid giving you N2O gas plus 2H2O liquid. Delta H naught will be equal to delta H naught formation of products minus delta H naught formation of reactants. Therefore, delta H naught of the reaction will be equal to delta H naught formation of N2O plus 2 into delta H naught formation of H2O minus delta H naught formation of ammonium nitrate, that is NH4NO3, which is equal to minus 81.46 plus 2 into minus 285.78 minus 367.5 equal to minus 122.56 kilojoules. As you know that delta H is equal to delta E plus delta N RT, where delta N is the change in number of moles, that is delta N is number of moles of products in gaseous form minus number of moles of reactants in gaseous form. Here delta N is equal to 1 and R is equal to 8.314 into 10 to the power minus 3 kilojoule per mole per Kelvin. As temperature is 298 Kelvin, hence putting all the values in the equation delta H equal to delta E plus delta N RT, you will get delta E is equal to minus 122.56 minus 2.477, which is equal to minus 125.037 kilojoules. In thermochemistry, we discuss various types of enthalpies. One of them is enthalpy of combustion or heat of combustion. Enthalpy of combustion is the heat evolved when 1 mole of the substance, whether it is molecule or an element, is completely burnt, that is oxidized, in presence of oxygen. Enthalpy of combustion is always negative because combustion is an exothermic process. Here is an example: CH4 gaseous plus 2O2 gaseous giving you CO2 gaseous plus 2H2O. Here heat of reaction is equal to minus 890.3 kilojoule. Heat of reaction for this reaction will also be equal to heat of combustion or enthalpy of combustion of CH4, because CH4 is completely oxidized in this reaction. In another example, C2H5OH liquid plus 3O2 gas gives you 2CO2 gas plus 3H2O liquid. Heat of reaction is equal to minus 1367.4 kilojoule. Heat of reaction for this reaction will also be equal to heat of combustion for liquid ethanol, because 1 mole of ethanol is completely oxidized in presence of oxygen. In another example, you can see 2C2H6 gaseous plus 7O2 gaseous gives you 4CO2 gaseous plus 6H2O liquid. Here delta H for the reaction is equal to minus 745.6 kilocalories. Here heat of reaction will not be equal to the heat of combustion of C2H6, that is ethane, because 2 moles of ethane are completely oxidized. Therefore, heat of combustion for ethane will be equal to heat of reaction divided by 2, that is minus 745.6 divided by 2, which is equal to minus 372.8 kilocalories. Therefore, heat of combustion for ethane will be equal to minus 372.8 kilocalories and not minus 745.6 kilocalories. In another example, you can consider two reactions for the oxidation of carbon. First one is solid carbon plus half O2 gaseous giving you carbon monoxide gaseous. Here delta H is equal to minus 26 kilocalories. In the second reaction, solid carbon plus O2 gas giving you CO2 gas, and delta H for this reaction is minus 94.3 kilocalories. Both of these reactions are the reactions for oxidation of carbon, but heat of combustion for carbon is not equal to minus 26.0 kilocalories because carbon monoxide formed in this equation can further be oxidized to give carbon dioxide. Hence, heat of combustion or enthalpy of combustion for carbon is equal to minus 94.3 kilocalories. Here is an example to correlate heat of formations of the substances and enthalpy of combustion. The standard molar heats of formation of ethane, carbon dioxide and liquid water are minus 21.1, minus 94.1 and minus 68.3 kilocalories respectively. Calculate the standard molar heat of combustion of ethane. The required chemical equation for this will be 2C2H6 gaseous plus 7O2 gaseous giving you 4CO2 gaseous plus 6H2O liquid. Delta H naught for this reaction is not given. As the equation involves 2 moles of C2H6, hence the heat of reaction will not be equal to the heat of combustion for C2H6. So, the heat of combustion for C2H6 will be equal to heat of reaction divided by 2. To calculate heat of reaction, we can use the relationship delta H naught equal to delta H naught formation of products minus delta H naught formation of reactants. Hence, you will get delta H naught equal to 4 into delta H naught formation of carbon dioxide plus 6 delta H naught formation of H2O minus 2 delta H naught formation of C2H6 plus 7 delta H naught formation of oxygen, which is equal to 4 multiplied by minus 94.1 plus 6 multiplied by minus 68.3 minus 2 multiplied by minus 21.1 plus 7 into 0. It is equal to minus 376.4 minus 409.8 plus 42.2, which is equal to minus 744.0 kilocalories. This is equal to heat of reaction, but heat of combustion of C2H6 will be equal to heat of reaction divided by 2. Hence, heat of combustion of C2H6 will be equal to minus 744.0 divided by 2 equal to minus 372.0 kilocalories. In the end, let us revise what we have discussed today. We discussed various factors which influence heat of reaction. We defined heat of formation and enthalpy of substances and enthalpy of combustion also. We practiced some examples related to enthalpy of formation and enthalpy of combustion. In continuation, in next lecture, we will discuss some applications of enthalpy of combustion.